10 years ago, in 2015, we heard the universe for the very first time. We heard a chirp through the faintest tremble in the fabric of space. Gravitational waves, once a prediction of Einstein's theory, had finally been detected in an event labelled GW 150914. It was a moment that shook the universe and changed the foundation of physics forever. But what many don't realise is that Australia was listening long before that cosmic chirp arrived. From the earliest days of gravitational wave science, Australia played a vital role, contributing groundbreaking research and innovation before, during, and after the historic first detection. This is the story of how Australia helped pave the way to that discovery, how we've shaped gravitational wave science since, and where we're heading next. Gravitational waves are ripples in space-time created by some of the most violent events in the universe, including colliding black holes, merging neutron stars, even exploding stars.
Gravitational waves is essentially a completely different type of messenger compared to electromagnetic waves and lights that essentially travel across the whole cosmos undisturbed.
For decades, scientists tried to detect them. And then, on September 14, 2015, it happened. In a distant galaxy, 1.3 billion light years away, somewhere in this part of the sky, two black holes, once caught in a cosmic dance for billions of years, finally fell into each other, sending ripples through the universe.
So this is crazy to picture these 30 solar mass objects moving at about 60% the speed of light, whipping around so fast that they make a blur. The gravitational waves traveled at the speed of light until they reached Earth, and we detected them with LIGO. But the signal was just a few tenths of a second long, so a very short signal.
Those ripples were heard by LIGO's detectors in Livingston, Louisiana, and Hanford, Washington, USA. And Ozgrad postdoc Natsuni Kibunchu was in the room where it happened.
Yeah, so I was actually on shift when it happened. I was sitting in control room. So at that time, we had an out-shift operator, one at Livingston, one at Hanford. So at Hanford, that was me. So Corey Gray was the guy before, on shift before me. He left the detector lock, so there was not much that I had to do. I just babysat the interferometer. It was really quiet. And I heard a TeamSpeak call. And because we were in an engineering run during the time, we have a control room channel on TeamSpeak, and Livingston operator and their commissioners talk all the time. So I'm used to hearing this two-way conversation, so I just tune it out. It turned out to be that night a German scientist called to check up on the site because he noticed something in the signal in the pipeline. And he was calling to see if everything was working all right. I totally ignored him. At the evening of that day, my friend texted me if I was walking around with the slide whistles making noise, because apparently there was something. Yeah, there was a lot of investigation going on, what's going on at the site around that time. People really want to make sure nothing malicious was happening.
For this first gravitational wave detection, it got vetoed, and we thought that it was just noise and we're going to throw it away. And so when I first looked at it, I thought it looked very similar to a lot of the detector noise that we see. And so I didn't really think it was real. And I was like, no, it's not real. It's not going to be real.
You see, LIGO had a team whose job was to secretly inject faked signals into the data, blind injections, to test the system. Their goal was to make sure the collaboration could identify a real signal even if they didn't know it was fake. So when GW 150914 appeared, the first question was, did the injection team do this?
So this was really important when we first detected gravitational waves, and we had never detected them before. We wanted to be absolutely sure that what we detected for the first time was coming from space. It was actual stretching of space-time. People came up with this idea of injecting fake gravitational wave signals into the detector by physically shaking the mirrors in the LIGO arms in the way that would mimic the way a gravitational wave would do it. We would do this regularly in order to check that everything worked. And sometimes this was done and everyone was told about it, but there were also what are called blind injections. So on blind injection, we would simulate a gravitational wave going into the interferometer. No one would know about it except for the blind injection team. And then we would find out if people could detect it without knowing that it was in the data. Fast forward to 2015, and we were still commissioning the detector. It wasn't fully operational yet. It was taking data, but we were still setting up some of these subsystems like the injections. We all got this email, and it said there was this interesting event observed in the detectors, and people were asking, oh, is this an injection? Did someone do an injection? Are we testing the injection systems? And I was running the injection systems. I knew we were not ready to do the injections yet. I knew that whatever that we had seen, this was, it could be real. It was definitely not a fake system, a fake injection.
The injection team confirmed it wasn't them, and quickly the truth emerged. This was no test. It was the first direct detection of gravitational waves.
GW 150914 changed everything. Not only, first and foremost, was it the first detection of gravitational waves approximately 100 years after Einstein's theory of relativity was written down, and after decades of work to make this a reality. It was also a weird signal at the time. We now know that these 30 solar mass black holes in 150914 are evidently common. But when this discovery took place, people didn't know that black holes merged with other black holes. This was an idea that maybe stars and binaries form black holes that merge, but whether or not this happened with a rate that high enough that you would ever see a merging binary black hole was unknown. So it was very exciting. It was the first detection of a binary black hole in any way.
Ladies and gentlemen, we have detected gravitational waves. We did it.
But while the world celebrated this groundbreaking moment, Australia's gravitational wave journey had already been decades in the making. Long before the first detection in 2015, Australian scientists were building detectors, developing theory, and laying the groundwork for what was to come.
Well, I think Australia has played a really significant role in shaping our community because we were there right from the start. There was David Blair with his Noah bar in the 1980s. So that was really the beginning of the field. And then, from the early 90s, we were involved in the experimental side. Australia's designed, developed, built, implemented and commissioned major components of the two LIGO detectors. We've been key developers of the LIGO data analysis system in the early days. We wrote a lot of it, but we've also now developed a lot of data products and data analyses. We've developed different analyses that they used and also developed a number of gravitational wave searches. So we've actually contributed a lot across the spectrum. And Australia is one of 4 countries that are partners in advanced LIGO. So we're already one of the key players in the system.
Before lasers and interferometers became the tools of choice, gravitational wave detection was a much more hands-on affair. In the 1970s, nestled in the bushland of Western Australia, a team led by David Blair was building something extraordinary, a cryogenic detector made from niobium, a metal that could ring like a bell. This was Australia's first gravitational wave detector, and it laid the foundation for decades of innovation.
When it came to, I did a PhD, which was in a pretty difficult area, involves superconductors and cryogenics and liquid helium and very precision experiments. But when it came to the end of that, I read something in New Scientist magazine about gravitational waves. I had never heard of gravitational waves. Then I was going to a conference in America on low temperature physics, and people were working on building cryogenic gravitational wave detectors, and it was following a person called Bill Fairbank. And I approached him and said, I want to join your team. I want to work on one of your difficult experiments. So then came the opportunity to come back to Australia, and I came back and said, I want to build a Southern Hemisphere gravitational wave detector. And while I was in America, I had discovered the amazing properties, or the amazing acoustic properties of the metal niobium, and that niobium would ring for longer than any other metal that we knew. And it was quite spectacular, this wonderful piece of technology that reached exquisite sensitivity. It was able to measure motions about the same as we measure in the new laser detectors that actually detected gravitational waves. Unfortunately, it was only 3 meters long, and we needed something 3 kilometers long. So it became fairly clear, even by the time we had this thing operating, that we had very little chance of actually detecting anything because it wasn't big enough. And then we built the facility at Gingin. The state government made this land available to us, a large piece of beautiful bushland, Banksia bushland, and we made agreements with the indigenous people to respect the land, respect the vegetation, and all sorts of things like that. That was when we started really focusing on the laser detectors and discovered lots of interesting physics, which was really essential to be making those detectors work.
The Gingin facility began as a bold vision as an Australian home for gravitational wave research. Today, it's a cutting-edge testbed for the technologies that power current detectors and those earmarked for the next generation of detectors. From precision optics to seismic isolation, Gingin is where theory meets experimentation.
We generally have 3 sort of main lines of research at Gingin. 2 are about optical cavities. One is we have a cavity set up testing the current technology for gravitational wave detectors. This is the technology like LIGO and Virgo. And then we have another cavity set up for testing what is the next generation of technology for gravitational wave detectors. Things like Einstein telescope, Cosmic Explorer, and the exciting Australian proposal for a NEMO gravitational wave detector.
From testing today's detector technology to prototyping the next generation, the research at Gingin is helping shape the future of gravitational wave science. But Gingin is just one node in a much larger network. In 2017, the ARC Centre of Excellence for Gravitational Wave Discovery, also known as OzGrav, was launched. This national initiative brings together researchers from across the country, uniting pulsar and gravitational wave communities into a single, focused program. Through OzGrav, Australian scientists and students have gained the opportunity to fully participate in gravitational wave astronomy on the international stage. With OzGrav bringing together researchers from across Australia, the stage was set for innovation. From the East Coast to the West Coast, scientists have been tackling the toughest challenges in gravitational wave detection. And what they have achieved is nothing short of extraordinary. At the heart of gravitational wave detection is light. But even the purest laser is subject to the laws of quantum mechanics. To push sensitivity further, Australian researchers turned to quantum squeezing, a technique that reshapes quantum noise itself.
The LIGO detectors are full of state-of-the-art technology. Whatever it is they use, it is the best in the world. And yet, their sensitivity is not as good as we would like. And so the question is, how does one improve on the best in the world?
The thing is, a laser beam, no matter how, we have to stabilize it so it has very pure power and pure phase. But no matter how well we do that, there's this intrinsic property of nature called quantum mechanics, which affects at that fundamental level how precise, how powerful, what the amplitude of a laser beam can be. Now, not only is the amplitude fuzzy, but something called the phase, how often the laser beam crosses zero. Now, if you look precisely again with a right down on the small scale, that phase is fuzzy due to quantum noise. Now, the gravitational wave detector are actually trying to measure phase differences. That phase difference imposed by a gravitational wave affecting the 2 arms of our interferometer differently. But if there's this fuzzy noise there, this fuzzy quantum noise, then that's going to minimize, or it's going to restrict how precise we can measure that phase difference. So that's quantum noise. Now, normally quantum noise is quite unimportant, But in a gravitational wave detector, what we're trying to measure in that very first measurement was a change in phase or a change in separation, which was 1,000th times smaller than a proton in a distance of 4 kilometers. Such a small change is right down in the realm where this quantum fuzziness becomes important. So this process called squeezing is like taking a balloon, squashing in one direction, stretching in the other. So we squash in the direction that we want to make a precise measurement.
Of course, squeezing quantum noise is only part of the challenge. The optics themselves, the mirrors, coatings, and lenses must be engineered to perfection. And when you're dealing with laser powers in the hundreds of kilowatts, even the tiniest imperfection can distort the signal.
The current generation of gravitational wave detectors are the first detectors that use quantum sensing to get an advantage that you can't get in any other way. And what I mean by that is, in often other systems, you can improve the signal to noise by, say, just bumping up the laser power, which is relatively cheap. In gravitational wave detectors, we've hit this barrier it's been very, very difficult to increase the laser power. And that's one way to increase the sensitivity, is by increase the laser power. But what ends up limiting it is all the thermal aberrations, where small amounts of absorption create lenses inside the detector and aberrations within all the optics that have to be controlled to an extreme degree.
High optical power has been one of the big challenges, and thermal noise obviously another big challenge for gravitational wave detectors. And so we're testing both the mirror coatings for lower thermal noise and the high optical power.
But it's not just light that needs taming. Gravitational wave detectors sit on Earth, and Earth moves. Seismic noise from earthquakes and even from distant traffic can drown out the signals we're trying to detect. In fact, a few hours after the first detection of GW 150914, an earthquake rocked the LIGO detectors, and a lot of information was lost due to that earthquake. At Jinjin, researchers are building isolation systems that let detectors stay still enough to hear the cosmos.
I have to say that for the Earth-based detectors, there is not much hope to completely remove this noise affecting the detector, simply because we can't. We live on the Earth and we have to live with that noise. What we can do is try to remove it as much as possible, to reduce it, to suppress it as much as possible. Why? This is because there are many objects that can produce gravitational waves in frequencies below 30 Hertz, for example, intermediate mass black holes. But also all the objects that are supposed to be discovered by the space-based gravitational wave detectors that are going to look in the lower frequencies. What we want to do with the ground-based gravitational wave detectors is to open a possible window as much as possible to detect those objects that can lie in the lower frequency window.
From quantum squeezing to mirror coatings, from laser power management to seismic isolation, Australian researchers are tackling gravitational wave detection from every angle. It's a testament to the diversity of expertise across Ausgrav working together to push the boundaries of what's possible. And while these innovations help us hear the universe more clearly, gravitational waves are only part of the story. Almost 2 years after the first detection of gravitational waves, another monumental signal popped up. And for the first time, we didn't just hear a cosmic event, we saw it too. And Australian scientists were ready to witness it. The detection of GW 170817 marked the birth of multi-messenger astronomy. 2 neutron stars in the galaxy NGC 4993 crashed together, sending ripples through space-time and light across the cosmos. And once again, Australia was ready to contribute.
Yeah, electromagnetic follow-up, that's when you get a gravitational wave that's been detected. It's in a certain position in the sky. So you get electromagnetic instruments all the way from radio up to high-energy gamma ray detectors. And they slew to that point on the sky to try and see if they can capture a little bit of light. And it's important because gravitational waves tell us about the mass and the motion of the sources, but the light gives us information about the explosion, about the mechanism or the physics.
Yeah, so I mean, in short, hands down the biggest event in transient astronomy history. There were 70 telescopes and all over the world, every continent, 4,000 astronomers, researchers working on it. Big. We were 14 of those 70 and had about 150 of those 4,000 researchers, so it was a big effort. We also were our location made it advantageous, so we provided very key information like some of the first spectra, early images. We actually pinpointed the location with radio detection and provided theory on what is going on.
The detection of GW170817 wasn't just a technical triumph, it was a scientific revelation. For the first time, gravitational waves and light were observed from the same cosmic event. But what did we actually learn from this event? And how did it reshape our understanding of the universe?
Yeah, 170817 was a really interesting event. So that was the very first gravitational wave detection of binary neutron stars. But what made it really phenomenal was that we got light for the first time from a gravitational wave source.
There were a lot of firsts. Okay, we were able to make the first, we pinpointed an actual location and object in a galaxy that created a gravitational wave event, because previously there were black holes and you weren't able to pinpoint those. We were able to confirm that kilonovae, these explosions, were actually associated with these neutron star merges, which was like 40-year-old theory, but never seen. So check, right? We're able to confirm that short gamma ray bursts are associated also with those, which is another 50-year-old theory. Check, right? We're able to confirm Einstein's prediction that gravitational waves travel at the same speed as light. It's because you have the gravitational wave and the light, so they both arrive. Look at that, right? So that's check. We're able to then explore those optical and infrared spectra to see that these kilonovae produce a lot of elements, and in particular really heavy elements. Like if you have the periodic table of elements, the ones down at the bottom that are weird names. Okay, so all these really heavy things, including things that we do know and love, like platinum, gold, and I don't know if europium is your favorite element, but but all kinds of different heavy elements are produced there, and that's also been a theory, and it helps to predict that. We also were able to use that one event to help independently measure the expansion rate of the universe. I mean, it goes on and on. There's a lot from that event.
GW170817 changed how we study the universe, combining gravitational waves and light to reveal more than ever before. But behind every detection and every breakthrough are the people who made it happen. These are the personal stories at the heart of Australia's gravitational wave community, what they experienced and how they felt when they heard the news of the first detection.
Well, it was funny. I actually heard about it because one of my students was actually at LIGO Hanford working on it, and they sort of told me that it happened. I just thought, wow, that's amazing.
Well, it's sort of a surprise and not surprise. And we sort of anticipated that. I was so sure that advanced LIGO can detect gravitational waves, but was surprised that so early. And we were so excited that we just really hard to contain our excitement, because before was sort of embargoed the recount to the broader community or even physics community. But we are so very, very much excited, and then also surprised that it's a black hole. It's a binary black hole. And it was, I would say, still one of the very high point in my career.
I was asleep. Probably. But then when I came in, you just saw there were emails flying around. And I actually had one of my grad students was at Hanford Observatory working on it, and she was one of the ones that was dragged out of bed to go and try and figure out what had happened. So it was a very exciting time.
Where was I? I was here in Canberra, and I was at home. It was in the evening. And at 9:15 p.m, I got a text from my daughter saying, Australia has a new Prime Minister. And this was Malcolm Turnbull ousting Tony Abbott. And I was kind of digesting all of that. Then I got this email from within, a small subgroup of our collaboration. And it said words to the effect of, there's been a very interesting signal in the LIGO detectors in the last hour. So I read that, I reread it, because that was quite strong language for us at the time. Anyway, I forgot all about the revolving door of prime ministers and focused on that. And as the minutes went on, it became evident that, that A, this was a very strong signal, but also that it was a strong detection candidate. So the story got better and better as the night wore on. And by midnight, I realized I wanted to tell someone. I had this burning desire. And I knew I couldn't tell anyone outside the collaboration. And then all the people here, I assumed by then, were asleep. So in the end, there was no one I could actually tell. And it made for this incredibly frustrated but very exciting, restless kind of night.
Well, I was actually, like many Australians, at home watching the fact that there was this huge event happening in Australia. It was deposing, our Prime Minister was sacked, basically. But then the news came through that there had been this signal that might have been seen by LIGO. And, of course, there was quite a lot of sort of skepticism back then. We'd never expected at that stage to see the first gravitational wave. We knew that we'd been experimenting with injecting false signals into the data just to show we could extract them. So, my first thought was it's probably one of these blind injections. So originally it was met with some, healthy skepticism. But as the days started to roll by, and it became clear that no, this wasn't a blind injection, that was a real signal. That's when it really hit, that the excitement that this first ever detection of a gravitational wave had occurred. This is one of the biggest events to ever happen in science.
It was an evening. So I have my computer. I can pull it up if you want. I saved some Skype messages that I sent to my colleague Paul Lasky. But after the email thread after the emails about the event, I wrote to Paul and I said, I think this thing might be real, but we have to be really careful. It certainly is the most promising candidate we've seen. But then, over the course of this conversation, by the end, we were pulling out bottles of scotch, and we were excited that this was the real thing, that all the effort up to that point was finally paying off.
These stories remind us that science isn't just about data, it's about people. The passion, persistence, and curiosity of Australia's gravitational wave community have shaped a decade of discovery. But the journey is far from over. As this community grows, so do its ambitions. With new technologies, new collaborations, and new questions on the horizon, researchers are already looking ahead. What will we discover next? What tools will we need? And how will Australia shape the next decade of gravitational wave astronomy?
We have been detecting too many black holes now. Neutron stars needs to show up. But what I really want to see is, so the special thing about gravitational waves is we always use the analogy of hearing the universe, right? So there is a period of the universe where optical telescope won't be able to penetrate. And gravitational waves can give us information from beyond that era. And this is what I would be the most excited about if we ever detect something like that. So it's the sound of the universe, right after the Big Bang, few 100,000 years after the Big Bang. That would be awesome.
The most exciting part is the unknown, with the thing that we not yet discovered yet.
Australia has already has a long history or tradition of contributing advanced technology and expertise to the international gravitational wave community. I think we will continue to play a key role in the future for the next generation ground-based gravitational wave detectors. We are largely involved in the Cosmic Explorer and Einstein telescope community, and we have been working together with international scientists and groups on the ideas and development of technologies for the next generation detectors. Building a next generation detector in Australia is kind of a dream of many people in Australia gravitational wave community. And the Australia gravitational wave community is actually actively exploring the possibility and opportunities to host such a future generation detector in Australia. So I really look forward to that. And I hope that will be true.
So the biggest challenge is to have enough gravitational wave detectors. There's about 20% of the time when there's only one gravitational wave detector working, and then you won't know where the gravitational wave comes from. If we had an Australian gravitational wave detector, then that would help us pinpoint the gravitational wave source on the sky.
By the time my career is in its twilight, I would love for Australia to have its own gravitational wave detector. It would be amazing. We've already done an amazing job of growing the Australian community. So when we started, gravitational waves was a little brother, a little sister to the other astronomers in the country. And it's amazing the growth that there's been in this field and seeing young people coming up through our system today.
I'm excited to keep pushing the detectors forward with instrumentation and just sort of see the push really far back into the earlier universe and see what we can see back there, get a first measurement.
I'm most excited for the next generation of gravitational wave detectors. They'll be so much more sensitive, and I'm really excited to do some cool new science with all that new data.
I'm excited to see when the space detectors launch, and hopefully we'll see like a background of just events. There'll be so many events that like we have the new problem of trying to filter them out.
I'm excited about Einstein telescope because of the triangle shape, which is quite insane.
I'm looking forward to seeing all of the crazy techniques that people will come up with for new detectors to try and optimize quantum noise reduction and everything else.
I'm really excited to see where the new R&D development for upgrades to detectors will spin off to other outside of gravitational wave research.
I'm excited about as the detectors get more sensitive, being able to detect cool, new and interesting things.
I'm looking forward to basically a lot of the development towards the next generation of detectors. It's really exciting. We got bigger, higher power, lots of stuff like that.
The new and interesting ways of dealing with detector noise and how they're going to approach that in future detectors.
I'm excited for hopefully when the detectors become more sensitive, we get to see a lot more neutron star collisions, neutron star collisions, because I want to know about the density of neutron stars in the universe. We don't know.
The universe is still full of surprises. In just 10 years since the first monumental detection, GW150914, gravitational wave science has transformed how we explore it, and Australia has been there every step of the way. As we look into the future, one thing is certain: the next wave of discovery is coming, and we'll be listening.